Hi everyone, welcome back to hydrocarbons. Now, this will be done a wee bit different from the last couple of weeks, just the way the topics have worked themselves out. So, for this week, between Monday and Thursday, we're going to be looking at isomers. So, for our learning intentions and success criteria, we're learning about isomers, and by the end of this section, we'll be able to state the definition of isomers, identify whether molecules are isomers of each other, and apply our knowledge to successfully draw and name isomers of molecules. So let's start off by thinking what they actually are. So the definition of isomers are compounds which have the same molecular formula but different structural formula. So let's have a wee think about what this means. So this tells us the molecules have the same total number of carbon and hydrogen atoms, but they're arranged in a different way. They don't join together the same. Now, it's important to note that isomers might belong to different homologous series. So, for example, if you've got alkenes, isomers might not only be alkenes. Okay? And also, isomers usually have different physical properties. Now, I've popped this little note here. At the start of the hydrocarbons topic, we learned the definition of a homologous series. And it is really, really important that you're able to define isomers and define homologous series and not get them mixed up. Commonly, people get them mixed up because the wording starts to sound a wee bit similar, so just make sure you're definitely happy with the difference between isomers and homologous series. So if you pause here, you can either copy down or print out and stick in the handout which is on Microsoft Teams. Okay, so we're now going to go on and have a look at identifying isomers. Now, for us to do this, there are two things we must consider. So the very first thing we do is assess whether the molecules have the same molecular formula. So in order to do this, all we need to do is count the number of carbon and hydrogen atoms in the molecule. So if you're given the structural formula, you count the carbon and hydrogen atoms. If you're given the name, then you can use your knowledge of the homologous series we've learned so far and the general formula to write the molecular formula. The second thing we have to do is assess whether the molecules have different structural formula. So this might be really obvious. So for example, if you've got an alkene and a cycloalkane, it's clear that their structure is different. One's a chain with a double bond, one is in a ring structure. Sometimes it's not quite as clear. So if it's not quite as clear, then what we do is use our naming rules to name the molecules. Now the rule is if it's got a different systematic name, then it has a different structure, and that will tell you then it's got a different structural formula. This will make a wee bit more sense when we start to look at examples, okay? So again, if you pause here, we can either copy this down or stick in the handout. Okay, so let's now look at some examples. So example 1, we're to decide if the following molecules are isomers of each other. So the very first thing we do is work out our molecular formula for each. So if we look at the left hand side and we count the carbons and hydrogens, we should get C6H14. If we do the same for the molecule on the right, we should get C7H16. Our molecular formula are not the same, and so these cannot possibly be isomers. Okay, so let me just reiterate that for you. They have a different molecular formula, they can't be isomers. As before, we can either copy this down or stick in the handout. Okay, let's think about example 2 now. Decide if the following molecules are isomers. Again, we start by working out our molecular formula for each. So the left we have C4H8, the right we have C4H8. Now if we think about our naming rules, we've got to consider the position of the double bond here. So in the left molecule, the double bond is attached to carbon number 1, and so we would call this but1ene. Remember, but because there are 4 carbons, ene because there's a double bond, 1 because the carbon to carbon double bond is on carbon number 1. In the second molecule, we can see the double bond starts on carbon number 2, so we would call this butene. So we can see we've got the same molecular formula, but a different name, and we know that means there's a different structure. Now you can see that clearly because the double bond is not in the same position. So this means we do have isomers of each other. Now a general rule is that if you have alkene molecules and the double bond is in a different position, they are always isomers of each other. There we go. So as before, copy this down or stick in the handout. Okay, on to example 3. Decide if the following molecules are isomers. So, molecular formula first. On the left we have C6H12. And on the right we also have C6H12. Now, it looks pretty obvious that the structure is different, but let's just go through the naming rules anyway, okay? So on the left, we have an alkene because there's a double bond. There are 6 carbons, and the double bond starts on carbon 2. That would be hextuene. On the right hand side, we have 6 carbons in a ring structure. That would be cyclohexane. And so again, we have isomers. Now another general rule is that alkenes and cycloalkanes are always isomers of each other. Now this makes sense if we think back to when we introduced the homologous series. They both have a general formula of CnH2n. So if you've got an alkene with 4 carbons or a cycloalkane with 4 carbons, they'll always have the same molecular formula. Okay, so copy this down or stick in the handout. Okay, on to example number 4. So starting off, we're going to look at our molecular formula. So on the left, if we total our carbons and hydrogens, we have C5H12. On the right, we also have C5H12. So they've got the same molecular formula. We now need to look at the naming. So on the left, we have 5 carbons, all single carbon bonds in a straight line, so that must be pentane. On the left, we can see that there's a branch. And so if we follow our naming rules by finding the longest chain, numbering the carbons in the longest chain, we should work out that the name of this is 2-methylbutane. So we can see we've got the same molecular formula, but the structures are different. On the left, we've got a straight chain alkane. On the right, we've got a branched alkane, and we can see that from the names. So again, we have a pair of isomers here. So another general rule, that straight chain and branched hydrocarbons are isomers of each other. Now this only rings true if they've got the same molecular formula, obviously. So again, if we copy this down or stick in the handout. Now we're going to look at a couple wee tricky ones now. So we're trying to decide if the following molecules are isomers in example 5. So if we run through, same as normal, and work out our molecular formula first. On the left, we have C7H16. On the right, we also have C7H16. So they've got the same molecular formula, so now we've got to start looking at the structure. Now in this case, it's definitely the best idea to go through our naming rules. So on the left, if we look, we've got a longest chain of 6 carbons, and we've got a methyl branch on carbon number 2, so we would call this 2-methylhexane. On the right, we have a longest chain of 6 carbons, and we have a methyl branch, and it again is on carbon number 2, because remember, we count from the end closest to the functional group or branch. So we would start numbering our chain from the right hand side. And so this molecule would also be 2-methylhexane. And because of that, they would not be isomers. Now if you were to look at this straight away, you would probably think same molecular formula but the structure is different. But actually these molecules are just mirror images of each other. The whole molecule has just been lifted and flipped over. Now it's a wee bit tricky to get your head round because they do look different at first glance. This is why we need to use our naming rules. And when you go and do tests and exams, these are the sorts of questions that come up which really test you. They're the more difficult ones. Okay? So make sure you're looking at your naming rules and not just at a glance. There we go. So pause here, same as before. Okay, on to our final example of identifying isomers. We're deciding whether these molecules are isomers of each other. So, as before, molecular formula first. On the left we have C4H10. On the right we also have C4H10. So now we've got to look to the structure and the naming. So remember, we look for the longest chain. And so if you look at the left, the longest chain bends round and is 4 carbons in a row. And so that molecule is butane. On the right, we can clearly see we've got 4 carbons in a row. So again, we've got butane. So these molecules are not isomers of each other. So while they look like they've got a different structure, the naming rules tell us otherwise. They're still arranged in the same way. The molecule's just been bent and twisted a little bit. That doesn't change the structure. It doesn't change how the carbons and hydrogens are attached to each other and joined. It's just changed the sort of formation of them. So remember, the longest chain doesn't need to be in a straight line. Again, this is another example of why we've got to use our naming rules if we're not entirely clear. Okay? So last example of identifying isomers, if we get this down in our jotters. Now the third part of our success criteria was looking at drawing and naming isomers. So just a wee reminder of the rules we learned there. If the molecular formula is the same, then alkene molecules with a double bond in a different position are isomers. Alkenes and cycloalkanes are isomers. And straight chain and branched hydrocarbons are isomers. So let's look at a couple of examples. So example 1, we're asked to draw and name isomers of pent-1-ene. So pent-1-ene shown there. And we can see that the molecular formula of that is C5H10. We know that. So let's think about the rules we just learned. If we want to draw an isomer of pent-1-ene, one easy way we can do this is by changing the position of the double bond. So we could have pent-2-ene. Another rule we learned was that alkenes and cycloalkanes are isomers of each other, so we could also have had cyclopentane. Now these are not the only 2 isomers of pent-1-ene, but this is just to show you an example of changing the position of the double bond and going from an alkene to a cycloalkane. So all 3 of these molecules have the same molecular formula, but different structural formula. They're all isomers of each other. Okay, so again, get this copied down. Okay, on to our last example of this lesson. Draw and name isomers of butane. Now the very first thing we need to do is draw butane. So if we do that first, we've got 4 carbon atoms, 10 hydrogen atoms, and single carbon-to-carbon bonds. Now if we think back to the rules that we'd learned, an alkane doesn't have a double bond, so it's not an alkene, so you can't change the position of the double bond. Alkanes don't have the same general formula of as cycloalkanes, so we can't put it in a ring structure. So the only way we can get an isomer of butane is by converting it from a straight chain alkane into a branched alkane. Now currently we've got 4 carbon atoms. We still need to have 4 carbon atoms in the final molecule. So let's have a look at what we could draw. So the only isomer of butane is 2-methylpropane. So if we look here, we've still got 4 carbon atoms, we've still got 10 hydrogen atoms, but it's no longer all in one straight chain, we have a branch, okay? Now just a wee reminder here, to get it really stuck in your head, straight chain alkanes will have branch chain alkanes if the molecular formula between them is equal, okay? We get that copied down. So that's us completed this part of this week's lessons. So we were learning about isomers. We should now all be able to state the definition of isomers, identify whether molecules are isomers of each other by looking at the molecular formula and structural formula, and apply your knowledge to successfully draw and name isomers of molecules. Now we've got exercise 4 to be completed and submitted today, or this week. So this should be completed by Thursday the 18th of June. Same as normal, either email to me, upload as an assignment submission on Microsoft Teams, or complete in your class notebook. Okay? This exercise is out of 10. And as always, if you've got any questions or you're unsure about anything, please just email me and I'll be more than happy to help, okay?